All right. So you're in general physics one. Well, if you have, first of all, most of you are going, oh my gosh. And if you tell somebody that you do physics or doing in physics, they're going to say, oh my gosh, that's a very hard class. I'm going to tell you that the only part that's hard is in your head. Physics, we do physics all the time. In fact, we do more physics than we can actually write down. So that's and if you think about it, for those of you who do athletics, think about all the physics that's involved with whatever athletic sport that you have. My daughter is an equestrian, so she does English writing. She jumps. So not only is she doing the physics in her head for her, she's also doing it for her horse. Now, if I were to ask her to write that 10 step down on a piece of paper, that would be a little more difficult because there are too many variables. Okay, so physics is really about the fundamentals, how the rules of the universe are, and that's what physicists are looking for. They're trying to find the rules of the universe. I am not a high energy physicist, so I do not get into the little particles and the stuff that goes on. I start at the atom. That's where I play. I play from the atom, and I play in Earth type time signatures here, in space and dimensions. Things get really weird when you go really, really fast towards the speed of light, and they get really weird when you get really, really small. So, and when you start going into space, things get a little strange as well. But Earth is really great, and we like Newton because Newton figured out a lot of stuff, and we're going to play with Newtonian physics. But in order to do that, we have to set some ground rules. And the ground rules are that that we are going to use words sometimes, because the English language is a little bit sloppy back and forth. We're going to get a little bit of that. But we get those different pieces. But we'll use words intentionally, and we'll talk about those definitions. For example, displacement versus distance. That's going to be something that we're going to talk about here in a little bit. But then we also are pretty persnickety that things are and how we define things. So I'm going to write some things down. I'm going to write like the number 7. I'm going to write 365. I'm going to write 12. I'm going to write 27. 27 is an odd number to be writing down. But most of us, when I write down 7, you got an idea of what that means. But maybe not. All right, same with 12. You got an idea of what that might mean, but maybe not. 12 could be a dozen, 12 eggs. 12 could be 12 inches to a foot. 12 could be something else. The thing that's going to help us with this are units. So we're going to be using units, and units are going to help us define our world, right? So if I use 7, we think days in a week. If I use 365, we think days in a year. I use 12. I gave you several examples of 12. 27 is probably not one that you guys are familiar with, but it's one that you need to be familiar with as we go through things, because it's something that we're going to, when we start working with our units, it's going to become more evident. And 27 meters per second is approximately equivalent to 60 miles per hour. And the reason that I need to give you this 27 meters per second is because in physics, we're going to use meters, kilograms, seconds. We're going to be using the metric system rather than the English system. But we live in a world where we use the English system. That's where we live. So we're trying to figure out, well, is my answer right? Okay. If I'm calculating the speed of a turtle, and I get 47 meters per second, I'm probably going to say that's either a rocket-powered turtle or I've done something wrong in my problem. All right? That gives you that frame of reference. So knowing that 27 meters per second is roughly 60 miles an hour, it gives you that frame of reference into how I can do something or how I'm looking at things. So we want to be building those, what I call rules of thumb, right? When I'm thinking distances, we all have a pretty good idea. Most of us could probably, if I said draw a line that's 1 inch long, most of us could probably draw a line that's close to 1 inch long because we have that in our frame of reference. Also, if you didn't know, this distance on the human body is approximately 1 inch long. So that's where the inch comes from. And the actual inch came from the king's inch, you know, whatever his digit right there was, that gives you about an inch. A conversion factor that we have, if we do that, this is 1 inch, that is actually, and it's an exact, it's 2.54 centimeters. So most of us have conversion factors in our head. Most of us have those conversion factors that we have a lot of them. We don't necessarily have all of them, but we have them in our head. So our fundamental units, these are units that we deal with. Our fundamental units, those are going to be things like length. And when you guys are doing your homework, one of the things that you're going to do and one of the problems is you're going to do what we call unit analysis. And how the book is going to talk about length, it's going to give you an L. So it's going to be a unit of length. Things that are unit of length, we have meters, centimeters, inches, feet, yards, kilometers. Those are all units of length. Then we have units of time, right? And that is going to be a T. They're going to use a T for that in this chapter. And luckily for us, we do solar, or our time is based off of the rotation of the Earth, and our year is based off of how long it takes us to go around the sun. And so that helps us out a lot because we're all going to be consistent, whether we're in the metric system or in the English system, and we're going to use seconds. Seconds is our fundamental unit that for time, and then of course we've got hours, years, and those kinds of things. And then the other fundamental unit that we have is mass. And our book is going to use M. We're going to be using in physics kilograms. That's going to be our fundamental unit. In the English unit, you may think of pounds, but pounds is not a mass. Actually, the English unit is a slug. Pound is actually a force. And pounds are weight, and weight are forces, okay? Weight is forces, and we're going to learn about that. We're going to get there to that part. We're going to start talking about it, but pounds are actually a weight, not a mass, but it's easy to get back to that because weight is gravity acting on our mass. So in the English unit, it's actually a slug. So that just gives you an idea of where that goes. There is one other fundamental unit, but we don't use that in Physics 1. We don't use that fundamental unit in Physics 1. We use it later on, and that is charge. And charge is a fundamental unit, and it is a coulomb, and actually it works both for English and in the metric system. But when we're dealing with the problems that you guys are going to have, that we are looking at our units. And unit analysis in physics is going to save your time. That helps us all the way around. All our conversions, all of that stuff, when we work on a problem, that is going to be the idea. So let's do a unit analysis. So if I do something like speed, speed has got units of length divided by time. All right. We're also going to tell you that there's a difference between speed and velocity. We'll get there. But right now, they both have the same units, length divided by time. It's going to be in meters per second. Now, I did open up about force. Force has a unit of mass. In fact, for us, it's kilograms meters per second squared. That is going to be a Newton. And this is considered a derived unit. We're going to mix our fundamental units to give us another unit, and that's how we're going to get our derived unit. But force is going to be a mass, a length, and a time squared. Okay, so that's going to give us our mass and length and time squared. So one of the equations, and you're going to have a homework problem that asks you if this equation is correct. Don't worry about the fact that you don't necessarily know how to use that equation yet. Just know that we're looking at the unit analysis of that particular problem. So what we're going to say is that my position, all right, my position is equal to acceleration times time squared. Okay. Well, position is a unit of length. Acceleration is length divided by time squared. And time squared is here. These cancel out, and I get length on this side. I get length on this side. So the units will match. And that is the key. The units have to match on both sides. I can't add apples and oranges. We can only add apples and apples. So you might have something that looks like this. I got position is equal to velocity plus acceleration times time. Squared. Okay. If I do this, I get length is equal to length divided by seconds. We already did this one. I got length divided by time squared times time squared. Those cancel out. This can't be right because I can't add in my velocity. So what your homework problem is going to ask you is, it's going to give you something like this. You're going to plug in the units, and you're going to show whether or not it's correct or incorrect. And that is really going to help us out. So all of our numbers have units, unless it's a multiplier. Like we want 2 times the distance. Well, that 2 won't have units, but the distance will have units. It'll be meters, yards, miles, or something like that. So numbers have units. And as we go through physics, you got to keep track of your units. And units are going to be they're going to save you. So let's go back to our 27. Okay? Because this will get you ready for a couple of problems that you have. So our 27 meters per second, we're building our rules of thumb. And what we want to do, and we start out physics with something called estimates. All right, estimates. So I'm going to give you an estimate. In fact, I'll actually use my own personal data. I'll call up some of my personal data, because we all have personal data, because most of us have smartphones, a lot of us have smartwatches, a lot of us. Okay, so last night, my resting heart rate last night was 82 beats per minute. That was my resting heart rate last night. Now, we all know that the human body isn't like a clock, and it's not going to be stable. So let's estimate the number of heartbeats in 8 hours. I slept for 8 hours last night according to my app. So we're going to use my personal data. We've got that. So if I'm going to estimate the number of heartbeats in 8 hours, I need to know what a resting heart rate is. Mine happens to be 82. Some people, my dad, for example, his resting heart rate is like 60. Okay. A lot of athletes have resting heart rates that are really down. Babies' resting heart rate might be 90. So you have to kind of pick a number to see if that works. So we want 8 hours, and I've got 82 beats per minute. So, and we're going to do this 8 hours. I've got a problem. My units don't match, right? But I know that there are 60 minutes in 1 hour. So my hours are going to cancel, my minutes are going to cancel, and I'm going to get an estimate for beats. Okay, I'm going to get an estimate for beats. So I'm going to plug that into my calculator. I get 8 times 82 times 60. And I think that doesn't look right, but we'll try it again. 8 times 82. Yeah, that's 660 or 56 times 60. Yeah, that's what it came out to be. 360 beats. That's a lot of heartbeats. And that's at rest. No wonder why we use a lot of energy to exist. So that's an estimate. And the idea behind an estimate is to give you some things around that says, does this make sense? Does this answer make sense? Does this do things? So you've got one of the assignments that you have is applying physics in the real world. Apparently, people like Amazon and Google ask some weird questions. How many golf balls does it take to fill up a bus? And you're going, okay, how would I even come up with that number? Right? How would I come up with that number? And that's exactly what Amazon and Google are trying to figure out, is to come up with that number. You have an assignment that says, I want you to figure out how many baseballs in a 55-gallon drum. Now the fair's coming up, and I think the Oklahoma State Fair used to have baseballs in the back bed of some kind of like a Silverado pickup truck, and if you're the closest person to guess how many baseballs are in the bed of the Silverado pickup truck, they win the Silverado pickup truck. So I mean, we've seen these, but we've seen the guess how many jelly beans are in a jar. That's exactly what you're going to do, except now you're going to use baseball, but you're going to have to make assumptions, right? We got to make an assumption. One assumption for baseballs are, I can't just put all the baseballs into my drum because they have size and shape. So when you guys are doing your baseball estimate, what I'm looking for is the logic that you're using. You know, you're going to have to look up the size of a baseball. You know, you're going to have to calculate the volume of a baseball. Then you're going to have to make some sort of an assumption on how much dead space that we can't fill a baseball in a 55-gallon drum. And so what you're going to do for your homework assignment is you're going to turn in a 1-page PDF where you have calculated how many baseballs that you think can go into a 55-gallon drum. You want to use your references, all right? You want to use your references. Tell me where you got the dimensions of a baseball. Tell me where you got those things, and then come up with a methodology to give me an estimate for baseballs. This will be kind of your fact-checking exercise will be like that as well, because around the way there was a meme on Facebook that said that it said something to the effect of, there are more atoms in a teaspoon of water, then there are teaspoons in the Atlantic. Okay, great. Ocean. All right. Well, I set out to prove it. I fact checked that. But that's going to cause us to have to do some things that we need to know. In Blackboard, in those supplemental videos that I have, I've actually worked this all the way out so that you can actually see what the actual numbers are. But in order to fact check this, what do I have to do? Well, first of all, I have to know how many teaspoons of water are in the Atlantic Ocean. So I need a good estimate or a good reference value for the Atlantic Ocean. Turns out Noah has a value. Noah has a value. And it actually gives it to you in volume in kilograms cubed. So you have to convert the kilograms cubed into milliliters, because that a teaspoon, we can do a teaspoon is on the order of milliliters. Okay. And a milliliter is a cubic centimeter. So it's a centimeter cubed. 1 milliliter is actually 1 cubic centimeter. So you have to end up in milliliters. Well, that's easy enough. Then you have to figure out, okay, how many atoms are in my teaspoon? Well, if it's water, right? Water is H2O. And if we assume that all of our milliliter is water, we can calculate the number of atoms or the number of molecules. The number of molecules in a milliliter. And then we have to multiply by 3 because we have 3 atoms in our molecule of water. And it turns out it's only 1 order of magnitude different between the teaspoons in there, but it is an order of magnitude. So the statement is actually correct, but we go through a process to validate and fact check it to get you an estimate. So those estimates, the reason why we talk about estimates in physics is we want to give you that frame of reference so that when you start working our practical problems that we have, when we start doing those, we want to have some confidence that that number is correct or that number is right or we're in the right ballpark. You know, if I'm wanting to know that something's within my classroom versus something that's out there being in a football stadium. So that's why we do these estimates first. So unit analysis and estimations are really critical for what we're doing. The other thing that we're doing, and I have just enough time to introduce it, you do have a lot of different things in here. Now, the way we do physics is we hope that you've had some algebra. But we don't require you to have trigonometry, but we have to have trigonometry to do physics. It's just a fact of life. We got to have trigonometry to do physics. But I'm about to teach you the trigonometry that you're going to need to do physics. Trigonometry is based off of a circle or a triangle. All right. Here's my triangle. And we're going to use our right triangle because that's how these equations are developed. If I know any 2 sides and 1 angle, I'm going to be able to figure out how this all works. So we're going to give myself an angle here to work with. First thing that we know about right triangles is that if this is going to be side C, this is side A, and this is side B. We have that A squared plus B squared is equal to C squared. Good old Pythagorean theorem. We've probably been using that for a long time. Now, we're going to use sine, cosine, and tangent. These are just ratios, all right? They're just ratios. So if I want to find the sine of the angle, the cosine of the angle, or the tangent of the angle, that's going to be a ratio. And that ratio is the sine is going to be B over C. Now, if I do this as an X and a Y and an R, right? Like our book does, our book uses an X, Y, and an R. This is going to look like Y over R. Or, because one of the things that we do in physics all the time is we move our triangles. They're not X and Y's. So it's maybe easier to remember it like this. This is the hypotenuse. This is the opposite side. This is the adjacent side. This would be the opposite over the hypotenuse. Cosine is going to be A over C, X over R, or the adjacent over the hypotenuse. Tangent is B over A, or Y over X, or opposite over adjacent. Okay. And other things that we need to know is that the sum of the angles inside a triangle is 180 degrees. That's one of the other things we need to know. There are some other factors that we need to know, but if we start with this is really how we're going to get going. So I can do some fun things. So let's take a tree. There's my tree. I'm going to be standing 10 meters away from the tree. And I can use a phone app or something else. And I can actually measure this angle. All right. And I'm going to say that that angle is 16 degrees. This is the length of the shadow. I want to know the height of the tree. All right, I'm given that information and I want to know the height of the tree. Well, that's H. So if I have this information there, there's my angle. I have the adjacent side. This is known. My angle is known. But that's the side that's not known, and that's the opposite is unknown. Well, if I do that, I've got my opposite and adjacent. I have my tangent. So I'm going to use the tangent of the angle is equal to the height of the tree divided by the length of the shadow. All right, so I've got the things that I need in there. So this, if I multiply that, this is going to be the length times the tangent of the angle is going to be the height. So the length is going to be my 10 meters. Tangent of 16 degrees. One of the things that you'll want to do on your calculators, okay, is you want to make sure you're in degrees. So you want to set up, make sure you're actually in degrees, and I am. So I'm going to do the tangent first. I'm going to do the tangent of 16 degrees. It gives me that times 10, gives me that. And it tells me my tree is 2.87 meters tall. So we could actually calculate that. Now, as you guys are doing your homework, you have a problem very similar to this, except we don't know this distance. And you actually, what you have is two triangles, but you know this distance. So this distance we know, and then we have this angle, and that angle is going to be a little different. It's going to be like 15 degrees. And you want to still calculate the height. This is a two equation, two unknown problem. In Blackboard, you have several, thank you. You have several different videos where we solve that two equation, two unknown problem. You also have a help that says a two equation, two unknown tutorial. I built an app to help people with two equations, two unknowns, because we're going to do a lot of two equation, two unknown type problems. So that's something that you really want to practice with. So I encourage you over the next several days to go in there and look at those. And there are extra videos on that. There's extra PowerPoints on that. I've worked this problem. You'll see that in some of the other videos. So you have that. But that is something that if you feel a little disconcerted about your math, understanding how to do two equations, two unknowns is really, really helpful. And that'll help you a long way going forward. I know brains are full, so I'm going to stop there. Wanting to get you, so what we've done today is looked at our units. We started talking about unit analysis. You do have some videos on unit analysis as well. We looked at estimations. We introduced our trigonometry type functions that we're going to have. And we actually solved a trig problem in here. And we started talking about two equations, two unknowns. You do have supplemental videos. You've got some tutorials. You've got a few other things. But I'm going to stop there and open it up for questions if anybody has any.